right, it's amazing to see all of you. And this is the third time I'm at SwiftLeeds. I was lucky enough to be at the first edition in 2021 when everybody was still wearing masks. It's good to see a crowded house. Before we get started, I also need to tell you a story. And by the way, my heart rate is at 157. So just to give you an idea of how it feels like for a person who's given tons of talks, I still feel super nervous. So before we start, there is good news and bad news. So, good news first. I packed swag. So, Firebase docs, I know they're super popular. We also have a minifigure that you can assemble. I also packed Flutter stickers. So now you're wondering, what is the bad news? So the bad news is, I am here. Why is that bad news? It gets worse. That is not the Google office. Uh-oh. That's what I filed last night. The good news and the bad news is I only found out once I arrived in Leeds because it got stolen in King's Cross off the train. So I put it on the train in the luggage rack, sat down here, the thing literally 2 meters away from me. And I only noticed once I got here. It's good because I had some quality time to work on the slides. So if I get a call throughout the talk, I might need to answer it. But the good news is I still have stickers on me, so if you want to grab stickers, come find me afterwards. And with that, let's get into the talk. So the title of the talk is, Don't Call Us, We'll Call You. So, a little bit about me. I live in Hamburg. I work at Google. I'm a developer advocate on the Firebase team. And I create samples and videos, code labs, and all of that good stuff, because I like to teach, just like Daniel. This is a SwiftUI tutorial I built using Apple's Doxy interactive tutorials. And I get to record videos in amazing studios like this one. I also do live streams on my personal channel. And I have a newsletter. And there is the obligatory QR code. And you better scan that thing because I just mashed an avocado for it. So I'll give you a second. All right, there's more QR codes. So let's start with the basics. And with basics, I literally mean basic. So I was born in the year when the Rubik's Cube was invented or came to the market. So that dates me. And this probably was one of the first lines of code that I wrote. So let's do a little bit more. So now we have a nice endless loop. But let's turn this into something more exciting. We did have let back then, and you could use it to define variables. You didn't have to, but you can. So now we have a nice variable. It's add1. And now let's implement a nice loop. So we'll print hello world, then we'll increment the variable, and then we will see if it is equal to 5, and then if it's not, we'll just jump to 10. So this is a really nice loop, isn't it? Side note, I think you can see that BASIC is pretty close to assembler because literally this is just like comparing stuff and jumping around. So back then, we coined the term spaghetti code for that. But thankfully, somebody came up with the idea of how to implement a proper loop. So now that's no longer spaghetti code, and we call it structured programming. But I know this is a Swift conference, so let's take a quick look at how this looks in Swift. So we've got our nice for loop. It iterates over the numbers 1 through 5, and it prints hello world. And if we generalize that, we will see that this is for element in sequence, and then do something with element inside the for loop. So let's quickly talk about what is a sequence or sequence. Funny enough, both American and British English have the same phonetic transliteration. So a sequence is a particular order in which related things follow each other. It's also a set of related events, movements, or items that follow each other in a particular order. So you can see that there is order and things and events, and they are somehow related to each other. So let's take a closer look at how this works and how it relates to the code that we just saw. So here we have our for loop, and down there you can see the elements 1, 2, 3, 4, 5. They are part of a sequence, and you could think of this as an array. It could be something entirely different, though, right? So, for example, all of those cities have one thing in common. They have great Swift conferences. And they are a sequence of strings inside an array. So we can use the same for loop to iterate over this sequence. So now you're wondering, why? Why are we talking about this? It's flashing a little bit. I don't know why. It's not, I didn't put that in my slide deck. Okay, so why? And to understand why, let's talk about asynchronous events, because that is something that we all should care a lot about. So back when I had my first computer, it looked something like that. Blocking was okay because everything happened synchronously, right? So you had a program, and in your program, if you wanted to get user input, you would halt the program to wait for the user input. So nothing else would happen. Like literally, the screen would freeze with the prompt, and the program would wait for the user to type in their answer, and then it would continue. On the devices that we carry around in our pockets, our supercomputers in the pocket, blocking is not okay, because the application must not freeze. If you'd freeze for waiting for user input, for example, or if you'd freeze if you make a network call and then you wait until you get the response back, the entire application would freeze, and the user would probably get very upset and then kill your application. So that is not a good idea. So we must not freeze, and that means that all the stuff that's happening happens asynchronously, or needs to happen asynchronously. So let's talk about asynchronous events, and I'm going to walk through history lane, and we're going to look at all the ways how you could handle asynchronous events in the past, decades almost. So we're going to look at delegates in Objective-C, callbacks in Objective-C, delegates in Swift, callbacks in Swift, combine, and structured concurrency. So when I built this application yesterday, I was not fully aware of how related it was to my situation, but there we go. So it's a little application that allows me to track the current user's, the user's current location. It's got this nice compass at the top, and we see the latitude, longitude. There's even the altitude and the accuracy. And there is a button that comes in very importantly, because when I tap the button, we will see where we are. And you all need to pay attention to where all those sample locations are, because I will be giving away swag, either stickers, or I'm going to send it to you for whoever gets the correct location. So let's start with delegates. So Objective-C delegates look a little bit like this. So we have the CL location manager, and this is really just like a tiny piece of this protocol here. And you can see that it says we have a location manager, and we have the method called did_update locations. And when this method gets called, it receives the manager. It also receives a pointer to the collection, to the locations that the location manager wants to send to us. So that is our protocol. And in order to implement this protocol, and in order to get all those location updates, you need to implement the protocol. So here's how that looks like. So we have our own location manager, and first up, we've got a method for actually starting to listen to the locations. So we'll call request when in use authorization. That's an actual method name. And then we'll call start updating location to get all those updates. So we're basically telling the CL location manager, hey, can you please tell me whenever there's a location update? And the CL location manager says, sure, I'll do that. And then whenever there's a location update, it will call this method here, sending in a reference to itself as well as the locations, and inside we can do something with it. And you can see that inside we're calling our own delegate to transport this location update to the client. So here is a little diagram that I created yesterday. We've got our location manager, we set the delegate to self, and then we ask it to check the permissions, then we start the location updates, and then whenever there's an update, we get callback by the location manager. We can do something, and then we can call our client back. So there's a lot of calling back from one part to the other. All right, so first location. Anybody has any idea where this is? King's Cross? Someone else? No? Cupertino? You're right. See me afterwards for swag. All right, so we're jumping over callbacks in Objective-C because we live in the modern world, so let's look at Swift. So how do you implement delegates in Swift? It looks very similar. We've got our CL location manager delegate up here, so our class conforms to this protocol, and we've got the same start updating method to kick off the process to receive updates, and then we get called back to this method here, and then we can do something with it. And what we do inside is we'll pick the last location and assign it to the location property. And then because this class here is observable, we can use it in SwiftUI and update the UI. And again, this looks very similar to the same sequence diagram that we had for delegates in Objective-C because nothing has really changed, just the language. And again, here is a location. So any guesses where this is? It's in a different location. Leeds? That's correct. I don't think it's the wheelhouse. I think it's the university. Nice. See me afterwards for swag. So let's go to callbacks in Swift. Again, we've got our CL location manager delegate. And then in here, what we're doing, we're not saving the location that we receive to a local property, but we're calling this other method here called onLocationUpdate, and we're passing the last location. And that is a true callback. And here is our client implementation. We've got our location manager with closure that we're instantiating. We're registering for updates up here. And then inside this closure, we get the locations and we store them on this local property. Please don't judge the code in terms of, if this is well written or, if you would actually do this in your app. I'm just trying to explain the principles here. So Here is how callbacks work as a sequence diagram. It's really hard for me to read because it's really small, so you'll probably have to download the slides. But you can see there is a lot of back and forth, and then at one point, we'll call our client from our location manager. Again, here is a location for you. Where's this? Hamburg? Nope, close. Amsterdam. No swag, sorry. Combine. All right, so show of hands. Who has used Combine in an app? Nice. Who's still using it in new apps? All right, so just the other day, I saw a really nice article where somebody, unfortunately I forgot the name, somebody explained how to use Combine to make sure that when you tap into an input field, the keyboard scrolls up, that there is enough distance between the keyboard and the input field, because the built-in keyboard avoidance framework doesn't give you that custom distance between the keyboard and the input field. And they're using Combine. So here is how you implement the whole thing in Combine. We've got our CL location manager delegate up there. And then we have a pass-through subject that has generics for CL location and error, so if something goes wrong. And that's, by the way, the first time that we're properly handling the error here. Then we've got the publisher, and that is the public thing. So it is connected to the subject, so the subject will route through, and then the client can subscribe to the publisher. And in our callback down here, in our delegate method, we will pass this on to the subject. So we're taking the location, sending it to the publisher, and the publisher publishes it for our client. And we can see that here. So this is our client, and we subscribe to the location publisher. We map the input as a location, then we catch any errors, then we assign that to a local property, which is, again, a published property. And don't forget to keep track of your cancellables so that you can properly clean up once this class goes out of memory. And here is how that looks like as a sequence diagram. And down there where you can see this tiny little twist, that is where we send it to our own publisher, and then it gets sent out of our class. Here's another location for you. Where's that? Say again? No? One more try?
London town.
London, yep. Oh, sorry, Turin. Did somebody say Turin? There you go. I didn't catch it up here, sorry. So, structured concurrency. Here is the same sample with structured concurrency, and we're using async await to do the whole thing. So wait, let me go back one step, because I didn't have time to do the highlighters. So here you can see we're using a continuation. So when we start the whole thing, we will get a continuation, we'll hold on to the continuation, and then whenever we get a callback from the location manager, we'll yield that to the continuation. So it's a little bit more complicated. And on the client side, this is how it looks like. So we'll have to call request single location using await. Here's how it looks like as a sequence diagram. Another location. Nope, Skopje. I know there's at least 1 or 2 people here from Skopje, so you should recognize that. All right, so here's a quote for you. You only get one shot in your life, and you might as well push yourself and try things. So why am I saying that? One shot, that's the keyword here. So this is a one-shot thing. So whenever we want to get an update, we'll have to call this. So we don't get this on a continuous basis. So using async await to do this kind of stuff is not the right tool for the job. So let's look at the right tool for the job, and that is async sequence. So an async sequence is a sequence that has generics over element and failure. So we can specify what kind of elements we have in our sequence, and for us it will be locations and an error type. So let's take a look at how to implement this with an async sequence. So up here, you see that we have an async stream that we're setting up, and inside the async stream, we get the continuation. And we'll use that continuation and store it, and whenever we get an update from Location Manager, we yield that to the continuation. And so it's very similar to what we do with the async await approach, but here, because it's a sequence, it can just like continue on and on and on. So, and here is how it looks like on the client side. So we start the update, and then inside our task, we will have a for loop that goes for, try, await, and then location update in location manager.location updates. So this goes on until we end the program or until this class goes out of scope. And whenever we receive an update, we can store it on the location. So let's take a look at how to apply this to something that I care about, Firebase. So you might know that Firebase has a bunch of products, and one of them is Cloud Firestore, which is a cloud NoSQL database, which stores document in the cloud. And it has a real-time feature. And the real-time feature allows you to continuously listen to a collection and receive updates from that collection. So whenever somebody changes something in the collection, you will receive an update. And here is the code you have to write in order to implement that in your client. So first, you'll set up a query, and in this query, we'll say, we want to listen to a collection called to-dos, because to-do list application is the go-to thing to implement, to explain stuff. And then we have our snapshot listener, and we set it up by attaching to the query and saying, we want to listen to any updates here. And the snapshot listener has a closure. The closure takes 2 elements, the snapshot and an error. When we get a snapshot, we'll iterate over the documents that are in the snapshot and then map them to take out the elements that are in there. So you can think of a document as a JSON array or JSON dictionary of sorts. So you'll want to convert that to your type-safe types in your application. So in this case, it's going to be a to-do. And then you must not forget to unsubscribe from this listener. So you'll need to remove it if your class got out of scope, or if the application ends, or if you want to stop listening to updates. So how about we were able to write it in this way? So here, we also subscribe to the to-dos collection, and we also map the document inside this compact map thing. But instead of having to set up our snapshot listener and taking care of all the housekeeping, we have just this one line here saying snapshots. And that is an async sequence that we subscribe to and which will receive all the updates on this collection. And then down there, you have your for loop where we iterate over all the updates that we get, and then we can assign them to a local property, and that property we can use in our UI to drive a list, for example. So here is how the implementation for that looks like. You can see that we define the snapshots function, and it returns an async sequence, and inside we set up an async throwing stream. So you might wonder, why do you return an async sequence when inside you're creating an async stream? The answer is async sequence is the protocol, so it's our blueprint that we want to adhere to, and the async stream, that is a utility of sorts that makes it easier for us to implement this whole thing without having to implement the whole sequence ourselves. So here inside we get a continuation, and then we will set up the snapshot listener just like before. And by the way, when I say we, this is not you, but we, the Firebase SDK team. So that is our implementation of implementing this sequence for you so that you don't have to do the work. So we add the snapshot listener, we listen to the snapshots, and then do error handling, map the documents, and yield them to the stream, and then you get the async sequence back. But there's one thing. If you listen to the documents that you store in the cloud, then you might not store the documents of just one user. If you're implementing an app just for yourself, that's maybe fine. You just store your own documents. But if you ship a real application, then you'll store documents of many users. And we want to make sure that you don't show my to-dos to Daniel or Daniel's to-dos to me, right? So you want to make sure you know who's the user, and that is why you need authentication. Firebase has an authentication module. It's called Firebase Authentication, obviously. And so we need to make sure that we know who the user is, and you do that by installing an authentication state listener. And the authentication state listener gets called back every time a user signs in or signs out. And we support a bunch of authentication mechanisms: email and password, email and link, sign in with Apple, sign in with Google, even Facebook and other stuff. And you can implement your own authentication mechanism as well if you need to support something that is custom to your business. So here we have an async sequence as well on the auth object, and it's called auth state changes. And what I do here, I run a compact map on it to take the input, which is a stream of users, of user objects, and then I just map to get the user ID. So now let's talk about how we can combine those two streams, because we want to make sure that our Firestore snapshot listener, or our Firestore stream in this case, knows exactly who is the signed-in user. So here comes our trusty flat map to take an input and then call something and return the result of that. And then we'll just move in the stuff that we built before. So that is literally the sequence that I showed you 3 slides before. And then we'll add this one little query parameter here, where field, to capture the user ID and make sure that our Firestore query only listens to documents that belong to that one user. Side note, that is only half of the story. You definitely also need to implement security rules, and they are a mechanism that makes sure that even if I somehow were able to hack into the system or make a REST call to the backend, I wouldn't be able to see your to-dos, and you wouldn't be able to see my to-dos, because the system verifies the authentication claim. But this is the part that you need in order to fetch the data. And then we can assign this to to-dos changes and use our for loop to iterate over all the changes that we receive, and then do whatever we please. For example, assign it to a property on our view model or inside the view, so that the view can get updated whenever there is an update on our collection. So let's take a look at what we've achieved. we've got this for try await to-dos and to-dos changes loop. So it's a simple enough for loop, but what we're doing is we're consuming an asynchronous stream, and it's just 3 lines of code, or 2. And we've come a long way from this for loop that I showed you in the beginning that was very, very basic and was the beginning of structured programming. So now you wonder why. Why is it called structured programming? And to answer that question, let's watch this. So structured programming shows you the world in a different perspective. So you might see it as just a simple for loop, in this case, but in reality, what you're dealing with is a complicated asynchronous algorithm under the hood, and all you have to care about is that your events are coming in as a sequence of events. So, what does structured concurrency do for you? It improves code readability because you don't have to set up complicated delegates that scatter handling of events across multiple places in your code. If you recall that, we had to set it up, we had to start the stream, we had to implement our delegate methods. And just imagine what happens if you have multiple streams of events that you need to synchronize, right? So if you imagine that you're not just getting location updates, but you want to use those location updates to also connect to a database and then fetch data and retrieve that data asynchronously as well using a delegate approach as well. So it's just like a giant mess of code, and using structured concurrency makes this a lot easier. It also simplifies error management because all you need to do is say that you might be throwing, and then at the call site you add your try statement to the for loop, and that's it. It eliminates callback hell and gets rid of spaghetti code, and it makes it so much easier to reason about your algorithms because everything is just locally contained. When I first saw the first asynchronous for loop, I was like, this looks really funny because it looks like a for loop. Is this the right, is this the right way to think about things? But yeah, it is, because it takes the concepts that we used for many, many years or even decades in structured programming and applies them to concurrency, which is a complicated enough topic. So anything that makes concurrency easier to use, that's a good thing in my books. Thanks.